Right now, as you watch this, for human beings are riding a spacecraft around the moon. Not in a simulation, not in a Hollywood soundstage, not in some aspirational concept video narrated over synthesizer pads. Right now, actual astronauts, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, are aboard the Orion capsule on the Artemis II mission, performing the first crewed lunar flyby since December of 1972. That was Apollo 17. That was 53 years ago. An entire human lifetime has passed since anyone saw the moon from this close with their own eyes. Let that sink in. More than half a century. We went to the moon 6 times, we walked on its surface, we drove a car across its dust, we hit golf balls into its craters, and then we just stopped. We turned around. We came home. And we didn't go back. Until now. And the question that keeps circling my mind, the question I think should keep circling yours, is not just why did we go back? It's what are we looking for that we couldn't see before? Because here is the thing about the moon that doesn't get said enough, that doesn't make it into the popular narrative, that gets buried under all the flag-planting mythology and Cold War nostalgia. We don't actually understand the moon. Not fully. Not even close. We've mapped its surface with centimeter-level precision. We've cataloged its craters with the obsessive thoroughness of Victorian butterfly collectors. We've brought back 842 pounds of lunar rock and soil across 6 Apollo landings and 3 Soviet robotic sample return missions. We've bombarded it with orbiters, impactors, and laser beams. And yet the moon continues to serve up mysteries that make planetary scientists lose sleep. Anomalies. Real, measurable, repeatable anomalies that challenge our models, contradict our assumptions, and occasionally make us wonder whether the story we've been telling ourselves about Earth's nearest neighbor is missing a few very important chapters. So let me take you through them. Not the fringe stuff. Not the conspiracy theories about alien bases and secret Nazi colonies and glass domes visible in enhanced photographs. I mean the genuine, peer-reviewed, argued about at conferences, published in Nature and Science scientific puzzles. The kind that keeps showing up in data from orbiters and landers and retroreflectors that are still sitting on the lunar surface right now, still bouncing laser beams back to Earth, still delivering information that makes us scratch our heads and reach for another cup of coffee at 3 in the morning. These are the anomalies that Artemis was designed to investigate. These are the questions that are pulling us back to the moon after 53 years of absence. Let's start with something you can't see with your eyes but can measure with exquisite precision from orbit. The moon's gravity. If the moon were a perfectly uniform sphere, the same density all the way through, the same composition from pole to pole, then its gravitational field would be smooth and featureless. A spacecraft orbiting such a body would trace a perfect ellipse, predictable down to the millimeter. But the moon is not a uniform sphere. It is a battered, asymmetric, geologically complex body, and its gravitational field is a mess. A beautiful, informative, deeply confusing mess. The first hint came in 1968, when 2 scientists at the Jet Propulsion Laboratory, Paul Muller and William Sjogren, were tracking the orbits of the Lunar Orbiter spacecraft. These probes were circling the moon to photograph potential Apollo landing sites, and their trajectories were being monitored with extraordinary precision using Doppler shifts in their radio signals. Muller and Sjogren noticed something strange. Every time an orbiter passed over certain large impact basins on the near side of the moon, Mare Imbrium, Mare Serenitatis, Mare Crisium, Mare Nectaris, Mare Humorum, the spacecraft would speed up slightly. It would dip toward the surface, pulled downward by an unexpected excess of gravity. Something dense was hiding under those ancient lava plains. Something that shouldn't have been there. They called them mascons, short for mass concentrations. And the name has stuck for nearly 60 years because we still don't fully understand what they are. Now, you might think the explanation is straightforward. Big asteroid hits the moon. The impact compresses rock. Compressed rock is denser. Denser rock means stronger gravity. Case closed. Except the physics of giant impacts says the opposite should happen. When a massive body slams into a planetary surface at tens of kilometers per second, it doesn't compress the target. It excavates it. It blows a hole, creates a basin. The crust thins out dramatically. Tens of kilometers of material gets removed. You'd expect a gravitational low over a major impact basin. a deficit of mass, a dip in the field. And yet there they are, enormous bullseyes of excess mass, some of them generating gravitational anomalies strong enough to measurably alter the trajectory of orbiting spacecraft. The mascon in Mare Imbrium, for example, produces a gravitational anomaly equivalent to having an extra slab of material roughly a kilometer thick spread across an area the size of France buried beneath the surface. The leading hypothesis involves a complicated, multi-stage process that unfolds over millions of years. First, the impact excavates a basin and thins the crust. Then, because the crust is now thinner, the denser mantle material beneath it rebounds upward, a process called isostatic adjustment, similar to what happens when you push a beach ball underwater and let go. The mantle pushes up into the void left by the excavation. Then, over the following tens or hundreds of millions of years, volcanic basalt floods the basin from below, filling it with dense lava flows that add even more mass. The combination of uplifted mantle rock and thick basalt layers creates a net positive mass anomaly, a mascon. It's a reasonable model. It's supported by some of the data, but it doesn't explain everything. It doesn't explain why the mascons on the near side are so much more pronounced than anything on the far side. The far side has impact basins too, including the South Polacan Basin, the largest and deepest on the Moon, but their mascons are either weak or absent. Why? If the mechanism is purely about impacts and mantle rebound, it should work the same way regardless of which hemisphere you're on. It doesn't fully account for the gravitational signatures detected by GRAIL, the Gravity Recovery and Interior Laboratory, twin spacecraft named Ebb and Flow that mapped the Moon's gravity field with unprecedented precision between 2012 and 2013. GRAIL revealed a subsurface picture far more complex and far more layered than anyone had anticipated. Beneath the obvious mascons were deeper gravitational structures, ancient buried impact basins, buried rift zones, density variations in the lower crust and upper mantle that bore no obvious relationship to surface features. The Moon's interior, it turns out, is not the simple, stratified, geologically dead place that textbooks had been describing for decades. It's a palimpsest, a document that's been written on, erased, and written on again, with older layers still faintly visible beneath newer ones. GRAIL also revealed something else. The lunar crust is pervasively fractured. Not just at the surface where you'd expect impact damage, but deep down, potentially all the way through in some places. The upper portion of the crust appears to be thoroughly pulverized, with a porosity of about 12%. That means roughly 1/8 of the volume of the upper lunar crust is empty space, cracks, voids, pores, fractures created by billions of years of relentless bombardment. The Moon is not solid rock. It's rubble, held together by gravity and habit. And those fractures have implications that reach far beyond mere structural geology, as we'll see when we get to the question of what's leaking out of them. But first, let me tell you about the single most surprising discovery of the last decade of lunar science, the one that overturned a consensus that had stood for 40 years. The Moon is not dead. I don't mean that metaphorically. I don't mean it in some poetic, the Moon is alive in our imaginations sense. I mean it literally. The Moon, which every science textbook from your childhood told you was a cold, inert body, a fossil world, frozen in geological time since the last volcanic eruptions petered out roughly 1 billion years ago, is still geologically active. It is still quaking. It is still cracking. It may still be venting gas. And the evidence for this has been accumulating quietly, almost sneakily, for years, hiding in datasets that nobody had the tools to properly analyze until very recently. The story begins with the Apollo seismometers. Between 1969 and 1977, the Apollo missions deployed a network of seismic stations across the near side of the Moon, at the landing sites of Apollos 12, 14, 15, and 16. These instruments operated for 8 years before NASA finally turned them off, and during that time they recorded thousands of moonquakes. Thousands, not dozens, not hundreds, thousands. Some of these quakes were easy to explain. Meteorite impacts produce seismic waves. You can actually use them to study the Moon's internal structure, the same way geologists use earthquake waves to image Earth's interior. Thermal quakes occur as the surface expands and contracts with the brutal day-night temperature cycle. The Moon's surface swings by roughly 300 degrees, Celsius every 29.5-day lunar day. And then there are the tidal quakes, caused by the gravitational tug-of-war between the Earth, the Moon, and the Sun, which flexes the lunar interior like someone repeatedly bending a metal coat hanger. But a significant fraction of the recorded events, the so-called deep moonquakes, didn't fit neatly into any of these categories. They originated from sources roughly 700 kilometers below the surface, at the boundary between the lunar mantle and what might be a partially molten core. They occurred in repeating clusters at the same locations, tied to the tidal cycle but not perfectly correlated with it. Their waveforms were peculiar, long, drawn-out, reverberant, as if the seismic energy was bouncing around inside a highly fractured, scattering medium for much longer than it would in solid rock. Some individual source regions produced quakes repeatedly over the entire 8 years of observation, suggesting deeply buried zones of persistent mechanical weakness, places where the rock yields again and again under tidal stress. What this tells us is remarkable. The deep lunar interior is still warm enough, still plastic enough to flex and fracture under gravitational stress. 700 kilometers down, the Moon is not a frozen, rigid ball. It's pliable, it's responsive, it's alive in the geological sense of the word. But here's where it gets really interesting. In 2023, a team of researchers led by Francesco Civillini at the California Institute of Technology reanalyzed the entire Apollo seismic dataset using modern machine learning algorithms and signal processing techniques, tools that simply didn't exist when the data was first collected in the 1970s. What they found was startling. Hidden among the known categories of moonquakes was a previously unrecognized class of seismic events. These were shallow, thermal origin quakes, but not the kind anyone had cataloged before. They appeared to be generated by the structural response of the Apollo 17 lunar module descent stage itself to the punishing thermal environment. The lander was expanding and contracting with the temperature cycle, producing tiny seismic signals that had been mixed in with genuine geological events for 5 decades. That might sound like a trivial housekeeping discovery. Oh, we found some noise in the data. How nice. But it's actually deeply significant because it means the Apollo seismic dataset is even richer than we thought. Once you strip out the instrumental artifacts, the remaining genuine moonquake signals become cleaner, sharper, more interpretable. The machine learning approach revealed subtle patterns in the timing and location of shallow moonquakes that suggest active geological processes are occurring much closer to the surface than the deep moonquakes imply. Processes that may be related to the lobate scarps that the Lunar Reconnaissance Orbiter has been photographing from orbit. And the lobate scarps are their own kind of anomaly, one of the most visually striking pieces of evidence that the Moon is still tectonically active. The Lunar Reconnaissance Orbiter, or LRO, has been circling the Moon since June of 2009, and in that time its cameras have taken millions of photographs at resolutions as fine as 50 centimeters per pixel. Among the many discoveries enabled by this extraordinary dataset, one stands out for its implications about the Moon's present-day geological state: the identification of thousands of features called lobate scarps. A lobate scarp is a type of thrust fault, a place where one block of crust has been pushed up and over another by compressive forces. On the Moon, these scarps appear as low, curved ridges, typically a few tens of meters high and several kilometers long. They look, from orbit, like wrinkles on the surface of an apple that's been left out in the sun too long. And that analogy is more apt than it sounds because the mechanism is essentially the same. The Moon is shrinking. As the lunar interior slowly cools, and it has been cooling for over 4 billion years, it contracts. And as the interior contracts, the rigid outer shell has to accommodate a smaller volume. Can't stretch, can't compress uniformly. So it faults, it buckles, cracks. The lobate scarps are the surface expression of this global contraction, and the LRO data suggests that the Moon has shrunk by roughly 50 meters in radius over the last billion years. That doesn't sound like much, but spread over the entire surface, it adds up to a lot of strain, enough strain to produce thousands of faults. Here's the key point. These scarps are young. Geologically speaking, they are astonishingly young. Some of them cut across small impact craters, which means the faulting occurred after the craters formed. Since small craters on the Moon are erased by micrometeorite bombardment on timescales of tens of millions of years, the scarps that cross them must be younger than that. Some may be less than 50 million years old. Some may be less than 10 million years old. And a few, this is the really provocative part, may still be active today. In 2019, a study published in Nature Geoscience by Thomas Waters and colleagues combined LRO imagery with the reanalyzed Apollo seismic data and found a statistically significant correlation between the locations of shallow moonquakes recorded by the Apollo instruments and the locations of lobate scarps photographed by LRO. The shallow quakes clustered near the scarps. This suggests that the faults responsible for the scarps are not just relics of ancient tectonic activity. They are still slipping, still releasing energy, still producing detectable seismic events. The moon, right now, as you listen to this, may be experiencing active faulting. Think about what that means for future lunar exploration. If you're going to build a habitat near the South Pole, which is exactly what the Artemis program envisions, you need to know whether the ground beneath you is going to shift. You need to understand the local seismic hazard. You need to know where the faults are, how often they slip, and how much energy they release. A moonquake strong enough to damage an inflatable habitat or crack a pressurized structure could be lethal. And we don't have enough seismic data to characterize the hazard. The Apollo seismometers covered only a tiny fraction of the near side. We have no seismic data at all from the far side or the poles. We are, in a very real sense, planning to build a house on ground we haven't properly surveyed. That's one of the things Artemis II and its successors will fix. The Artemis program includes plans to deploy a new generation of seismic instruments, smaller, more sensitive, longer-lived than the Apollo-era equipment, across the South Polar region and eventually across the entire moon. A global seismic network would be transformative. It would allow us to image the lunar interior in 3 dimensions, the way medical CT scans image the human body. We could map the size and state of the lunar core. Is it fully solid? Partially molten? Both? We could trace the deep moonquake source regions and understand what's happening at the mantle core boundary. We could detect and locate active faults and assess the seismic risk for future outposts. The scientific return would be enormous. But there's another reason to listen to the moon's interior, a reason that connects the seismology to one of the most provocative and persistent anomalies in lunar science: the question of what's coming out of the cracks. For centuries, literally centuries, astronomers have reported seeing brief, localized changes on the lunar surface. Flashes of light, temporary color changes, obscurations of surface features, patches of haze or mist that appear and vanish within hours or even minutes. These are called transient lunar phenomena, or TLPs, and their history is equal parts fascinating and maddening. The earliest credible reports date back nearly 1,000 years. In 1073, a group of monks at Canterbury Cathedral in England observed what they described as a splitting of the upper horn of the crescent moon, with fire and sparks emerging from the division. Some researchers have speculated that this might have been the impact event that created the crater Giordano Bruno, a young, 12-mile-wide crater on the far side that still has bright rays of ejected material spreading across the surrounding terrain. Others argue the monks were describing a meteorite entering Earth's atmosphere in front of the moon. The debate continues. In 1787, Sir William Herschel, the astronomer who discovered Uranus, reported seeing 3 bright spots on the dark side of the moon during a lunar eclipse. He interpreted them as volcanic eruptions. Coming from a less distinguished observer, such a claim might have been dismissed outright. But this was Herschel, the man who built the largest telescopes of his era, the man who discovered infrared radiation. His observations carried weight. Throughout the 19th and 20th centuries, reports accumulated. Red glows near the crater Aristarchus, temporary brightenings in the crater Alphonsus, obscurations in the area around the crater Plato, violet hazes near the limb. In 1958, the Soviet astronomer Nikolai Kozyrev obtained a spectrogram of the central peak of Alphonsus that he claimed showed emission features consistent with volcanic gas, specifically carbon-bearing molecules. The claim was controversial. The data was marginal, but it was published and it caught the attention of the scientific community. NASA took the phenomenon seriously enough to commission a comprehensive catalog. In 1968, Barbara Mittelhust and her colleagues at the University of Arizona compiled the chronological catalog of reported lunar events, which gathered over 570 individual TLP reports spanning 4 centuries. The The most frequently cited location was, overwhelmingly, the crater Aristarchus, a brilliant, relatively young impact crater sitting on the edge of the Aristarchus Plateau, one of the most geologically complex regions on the Moon. The plateau is a raised block of terrain scarred by sinuous rills, channels carved by ancient lava flows, and punctuated by volcanic vents. If any part of the Moon is still geologically restless, this would be a leading candidate. So are TLPs real? The honest answer, the scientifically honest answer, is probably some of them are. The problem is separating genuine lunar events from the enormous catalog of things that can fool an observer staring through a telescope at a bright object through Earth's turbulent atmosphere. Atmospheric seeing causes stars to twinkle, causes planets to shimmer. It can create false colors, false motions, false brightenings, especially near the limb of an extended object like the Moon, where differential refraction can split white light into its component colors. Many, perhaps most, TLP reports can likely be explained by atmospheric effects, observer fatigue, expectation bias, or simple misidentification. But not all of them. In 1963, astronomers James Greenacre and Edward Barr at the Lowell Observatory in Flagstaff, Arizona, observed reddish-orange color patches near Aristarchus that persisted for about 25 minutes. Their observation was independently confirmed by observers at Perkins Observatory in Ohio. In November of that same year, multiple observers at different locations reported a reddish glow in the same area. These were trained astronomers using good telescopes at well-established observatories. Their observations were coordinated and cross-confirmed. It's hard to attribute all of them to atmospheric artifacts. The physical mechanism most commonly proposed is outgassing, the release of trapped gases from the lunar interior through fractures in the crust. And here's where the seismology connects back. If the Moon is still seismically active, if its crust is still being deformed by tidal stresses and global contraction, then fractures are being opened and closed on a regular basis. These fractures could provide pathways for subsurface gases to reach the surface. What gases? Radon-222, for one. Multiple missions have detected radon in the tenuous lunar atmosphere, the exosphere, and its distribution correlates with regions of known geological fracturing. The Apollo 15 and 16 orbital spectrometers detected radon emanating from the edges of the Maria, where the thick basaltic lavas meet the older highland crust, exactly where you'd expect to find deep fracture systems. The Lunar Prospector mission, which orbited the Moon in 1998 and 99, confirmed these detections and added alpha particle data suggesting that radon was being released episodically, not continuously. Bursts of gas, intermittent venting, the Moon breathing. Other candidate gases include carbon dioxide, carbon monoxide, and water vapor, all of which have been detected in the lunar exosphere by various instruments. The sources could be diverse: solar wind interaction with the regolith, micrometeorite impacts vaporizing surface material, or genuine endogenic outgassing from the interior. Distinguishing between these sources is one of the major unsolved problems in lunar atmospheric science, and it's a problem that Artemis-era instruments are being designed to tackle. Imagine deploying a network of mass spectrometers across the lunar surface, instruments sensitive enough to detect individual molecules of gas as they escape from fractures in the regolith. Combine that with the seismic network I described earlier, and you have a system that can correlate outgassing events with seismic activity. If a shallow moonquake occurs near Aristarchus and, within hours, a burst of radon is detected at the surface, you've established a causal link between tectonic activity and gas release. You've explained the TLPs. You've solved a mystery that's been nagging astronomers since the 18th century. But gas isn't the only thing hiding under the lunar surface. There's also water. And the story of lunar water is one of the most dramatic reversals in the history of planetary science. 20 years ago, if you walked into a conference room full of planetary scientists and announced that there was significant water on the Moon, you'd get polite smiles and gentle redirection toward more promising research topics. The Moon was supposed to be bone dry, desiccated, more arid than the driest desert on Earth by many orders of magnitude. The Apollo samples showed almost no traces of water or hydrated minerals. The prevailing model of the Moon's formation, the giant impact hypothesis, in which a Mars-sized body called Theia slammed into the early Earth and blasted a cloud of vaporized rock into orbit, which then coalesced into the Moon, predicted total dehydration. The temperatures involved in such a collision would have been thousands of degrees. Any water present in the proto-lunar material would have been vaporized and lost to space long before the moon solidified. Except it wasn't. In 2006, a team led by Alberto Saul at Brown University decided to take another look at the Apollo samples using a technique called secondary ion mass spectrometry, or SIMS. This method can detect trace amounts of volatile elements, including hydrogen, which is a proxy for water, at concentrations as low as a few parts per million. Previous analyses had used less sensitive techniques and had concluded that the samples were dry. But Saul's team focused on something specific: tiny beads of volcanic glass. These beads were produced during ancient fire fountain eruptions, explosive volcanic events in which magma was flung into the vacuum of space as a spray of tiny droplets that cooled and solidified into glass before falling back to the surface. The beads are time capsules. They preserve the composition of the magma at the moment of eruption, including whatever volatile elements it contained, because the rapid cooling trapped them before they could escape. And when Saul's team pointed their SIMS instrument at these beads, they found water. Not much by terrestrial standards, roughly 46 parts per million in some samples, less in others. But the implications were seismic. The lunar interior was not anhydrous, contained water. Subsequent studies pushed the estimates higher. Some researchers argued that parts of the lunar mantle could contain water concentrations comparable to the upper mantle of Earth, up to several hundred parts per million. The bone-dry moon was a myth. The moon had been wet all along. We just hadn't been looking carefully enough. Then, in 2009, everything changed. NASA launched LaCrosse, the Lunar Crater Observation and Sensing Satellite, along with the Lunar Reconnaissance Orbiter. LaCrosse had one job: crash into the moon and see what came out. Specifically, the mission deliberately steered the spent Centaur upper stage of the launch vehicle into Cabeus Crater, a permanently shadowed crater near the lunar South Pole, a place that hadn't seen sunlight in billions of years, where temperatures hover around -250 degrees Celsius, roughly 30 degrees above absolute zero. The Centaur hit the crater floor at about 2,500 meters per second, excavating a plume of debris that rose above the crater rim into sunlight, where LaCrosse, following 4 minutes behind, flew through it, analyzed its composition with spectrometers, and transmitted the data back to Earth before crashing into the crater itself. What LaCrosse found was staggering. Water ice, lots of it. The concentration in the regolith at the impact site was estimated at about 5.5% by mass. That might not sound like a lot, but consider the scale. Cabeus Crater is 100 kilometers across, and there are dozens of permanently shadowed craters at the lunar poles, some of them even colder. If the water concentration detected by LaCrosse is representative, and subsequent measurements suggest it may be conservative, then the permanently shadowed regions at the lunar poles could contain hundreds of millions, possibly billions, of metric tons of water ice. Along with water, LaCrosse detected mercury, silver, carbon dioxide, carbon monoxide, ammonia, sodium, molecular hydrogen, methane, sulfur dioxide, and hydroxyl. The permanently shadowed craters aren't just cold traps for water. They're cold traps for everything. Any volatile molecule that wanders into those frigid shadows, delivered by a comet impact, outgassed from the interior, implanted by the solar wind, or produced by chemical reactions in the regolith, gets trapped, frozen, preserved, for billions of years. These craters are the deep freezers of the inner solar system, and they've been accumulating material since the moon's formation. And the discoveries kept coming. India's Chandrayaan-1 orbiter, which reached the moon in 2008, carried NASA's Moon Mineralogy Mapper, an imaging spectrometer designed to map the mineral composition of the lunar surface. In 2009, 3 papers published simultaneously in Science reported Chandrayaan-1's findings. Widespread hydroxyl and water molecules were present across the lunar surface, not just in the permanently shadowed regions. The signal was strongest at high latitudes and appeared to vary with the time of day, stronger in the morning, weaker in the afternoon, as if the water molecules were being created, destroyed, and migrating in response to the sun's position. The moon appeared to have a dynamic surface water cycle. This was confirmed in dramatic fashion in 2020, when NASA's SOFIA telescope, a 2.5-meter infrared telescope mounted inside a modified Boeing 747 that flew above most of Earth's atmospheric water vapor, detected unambiguous signatures of molecular water on the sunlit surface of the moon. The detection was in the Clavius crater, one of the largest craters visible from Earth with the naked eye. Water on the sunlit surface. Not just hydroxyl, not just in the shadows. Actual water molecules, present in concentrations of roughly 100 to 400 parts per million, embedded in the surface material or trapped inside tiny impact-generated glass beads. How does water persist on a surface exposed to the vacuum of space? Temperatures exceeding 100 degrees Celsius at local noon, and unfiltered ultraviolet and particle radiation from the sun. The current thinking involves a dynamic equilibrium between creation and destruction. Solar wind protons, hydrogen nuclei streaming outward from the sun at roughly 400 kilometers per second, constantly bombard the lunar surface. When these protons strike oxygen atoms bound in silicate minerals in the regolith, they can form hydroxyl, OH, and water, H2O, molecules through a process called space weathering. At the same time, solar ultraviolet radiation and micrometeorite impacts are constantly breaking these molecules apart. The net result is a thin, constantly refreshed veneer of water molecules on the surface. Not enough to form droplets or puddles, but enough to be detected spectrometrically and enough to slowly, steadily migrate toward the poles. The migration mechanism is thermal. Water molecules on the daytime surface are energized by solar heating. They deorb, they fly off the surface, and follow ballistic trajectories across the airless landscape, bouncing from point to point like tiny, invisible ping-pong balls. Each hop carries them a short distance, typically to a cooler spot. Over time, the statistical tendency is for molecules to migrate from warmer regions to cooler regions, from equator to poles, from daytime to nighttime, from sunlit slopes to shadowed hollows. The molecules that reach the permanently shadowed craters at the poles don't bounce out again. They're trapped. They freeze. They accumulate. This is why Artemis is going to the South Pole. This is why the landing site selection for Artemis III has focused obsessively on the region around Shackleton Crater, de Gerlache Crater, Connecting Ridge, Leibniz Beta Plateau, and other locations near the South Pole where permanently shadowed regions are accessible from sunlit landing zones. The water ice in those shadows isn't just a scientific curiosity. It's a resource, a strategic resource, a civilization-enabling resource. You can drink it, obviously, but more importantly, you can split it. Electrolysis, running an electric current through water, breaks it into hydrogen and oxygen. Oxygen is what you breathe. Hydrogen and oxygen together are what you burn in a rocket engine. The space shuttle's main engines burned liquid hydrogen and liquid oxygen. The upper stage of the Space Launch System, the very rocket that launched Artemis II, burns liquid hydrogen and liquid oxygen. If you can manufacture rocket fuel on the moon, you don't have to carry it from Earth. And carrying things from Earth to the moon is ruinously expensive, roughly $20,000 per kilogram, even with modern launch vehicles. Every kilogram of propellant you can make locally is a kilogram you don't have to launch from the bottom of Earth's gravity well. It changes the entire economics of space exploration. A lunar outpost with access to water ice doesn't just become a research station. It becomes a refueling depot, a gas station on the highway to the outer solar system. Spacecraft heading to Mars, the asteroids, Jupiter, or beyond could stop at the moon, top off their tanks with locally produced propellant, and depart with full fuel loads, something that's physically impossible if all the propellant has to come from Earth. The water ice at the lunar poles isn't just interesting, it's transformative. It's the key that unlocks sustained human presence beyond low Earth orbit. But before we can use it, we need to understand it. How much is there? How is it distributed? Is it concentrated in discrete deposits, like veins, or dispersed uniformly through the regolith? How deep does it go? Is it pure ice, dirty ice, or ice mixed intimately with soil at the molecular level? What other volatiles are trapped with it? How stable is it over time? Is it being lost to sublimation? Or is the cold trap so efficient that it's been accumulating without interruption for billions of years? These are the questions that Artemis III and its successors will begin to answer. And the answers will determine whether the moon becomes a permanent outpost of human civilization or remains a fascinating but impractical destination for occasional visits. Now, while we're talking about the surface, let me take you to something that you can actually see through a telescope. Something that has puzzled scientists for decades and that remains one of the most visually striking unsolved mysteries on the moon: the lunar swirls. If you look at high-resolution images of the moon's surface, the kind taken by LRO's narrow-angle camera, you'll notice something peculiar in certain locations. Bright, sinuous, intricately patterned markings that look almost like someone took a cosmic paintbrush and swirled white paint across the dark regolith. They're beautiful, they're bizarre, and they have no business being there, according to our standard understanding of how the lunar surface works. The most famous lunar swirl is called Reiner Gamma. It sits on Oceanus Procellarum, the largest of the lunar maria, on the western part of the near side. Through a decent amateur telescope, it's visible as a bright, tadpole-shaped marking against the darker basaltic plane. It's about 70 kilometers long and 30 kilometers wide. It has no crater at its center. It has no obvious topographic expression. It's not a hill, not a valley, not a ridge. It's purely an albedo feature, a difference in the brightness and color of the surface material that exists for reasons nobody has fully explained. But Reiner Gamma is not alone. There are dozens of recognized lunar swirls scattered across the moon, on both the near side and the far side. Some are associated with major impact features. The swirls at Mare Marginis and Mare Ingenii, for example, sit on the antipodes of large impact basins on the opposite side of the moon, suggesting a connection to the seismic energy focused through the lunar interior by these giant impacts. Others appear in locations with no obvious geological context. Here's what makes them genuinely anomalous. Every known lunar swirl is associated with a localized magnetic anomaly. The moon has no global magnetic field today. It lost its internal dynamo, the convecting metallic core that generates planetary magnetic fields, billions of years ago, probably within the first billion years of its existence. But it retains patches of residual magnetism, frozen into the crustal rocks from a time when it did have a functioning dynamo. These magnetic anomalies are weak by terrestrial standards, typically a few hundred nanotesla or less, compared to Earth's roughly 50,000 nanotesla global field, but they're real and they're measurable from orbit. And every known lunar swirl sits directly on top of one of these magnetic patches. The leading theory connecting swirls to magnetism involves the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of 400 to 800 kilometers per second. When these particles hit the unprotected lunar surface, they gradually alter the optical properties of the topmost layer of regolith through a process called space weathering. They implant hydrogen atoms, they reduce iron in mineral grains, they create nanoscale particles of metallic iron. Over time, millions to billions of years, space-weathered regolith becomes darker and redder. This is why mature lunar soil is darker than freshly exposed material in young crater rays. The theory proposes that the localized magnetic fields above the swirls are strong enough to deflect the solar wind, creating a miniature magnetospheric shield. The surface beneath the magnetic anomaly is partially protected from space weathering, while the surrounding surface is not. Over billions of years, this differential weathering creates a visible brightness contrast. The shielded areas remain bright, the unshielded areas darken. The swirls are, in essence, the magnetic field's shadow, or more accurately, its sunscreen marks, imprinted on the lunar surface. It's an elegant hypothesis. It's supported by laboratory experiments showing that magnetic fields of the right strength can indeed deflect solar wind ions. It's consistent with the spectral properties of swirl material, which shows signatures of immature, less space-weathered soil. But it has problems. First, the shapes don't always match. If swirls are simply the footprint of the overlying magnetic field projected onto the surface, their shapes should precisely mirror the field geometry. In some cases they do. In others, the swirl patterns are more complex and more finely structured than the magnetic field, as measured from orbit, can explain. This might just mean we need higher resolution magnetic measurements. The field may have small-scale structure that orbital instruments can't resolve. Or it might mean the deflection model is incomplete. Second, some magnetic anomalies don't have swirls. If the mechanism is purely about magnetic shielding from space weathering, every sufficiently strong magnetic anomaly should produce a visible brightness contrast. Most do, but a few don't. Why not? Is the field geometry wrong in those cases, pointing in a direction that doesn't effectively deflect the wind? Is the surface material different? Is there some additional factor we're not accounting for? Third, and most fundamentally, we don't know how the crustal magnetic anomalies formed in the first place. Or rather, we have too many hypotheses and not enough data to distinguish between them. Some researchers propose that the anomalies are remnants of the ancient global dynamo, frozen into the crust as it cooled through the Curie temperature of its magnetic minerals. But this should produce a relatively uniform distribution, and the anomalies are patchy and clustered. Others suggest that basin-forming impacts magnetize the surrounding crust through shock effects and plasma interactions. The enormously energetic vapor plume produced by a giant impact is essentially a conducting fluid moving through whatever ambient magnetic field exists, and this can induce strong local magnetization in the surrounding rocks. This would explain why some swirls cluster at basin antipodes, where focused seismic and impact energy might have enhanced the effect. Still others propose that some anomalies were created by the impact of magnetically rich asteroid material, iron-nickel meteorites carrying their own strong magnetic fields, which got imprinted on the target rocks during the violence of impact. Each of these models makes different predictions about the magnetic properties, compositions, and ages of the swirl-associated regions. Testing these predictions requires getting instruments, or better yet, astronauts with hammers and sample bags, onto a swirl and studying it up close. This is one of the high-priority science targets for the Artemis program and for robotic precursor missions. Reiner Gamma, in particular, has been repeatedly proposed as a landing site for a dedicated swirl investigation mission. If we can understand how and why these magnetic tattoos formed, we'll learn something fundamental about the Moon's early magnetic history, and by extension about the thermal evolution of its metallic core, which in turn tells us about the Moon's formation and early differentiation. Now let's go somewhere even more mysterious. Let's go to the far side. Every time you look up at the Moon, you're seeing the same face, the same craters, the same dark Maria, the same bright highlands. This isn't a coincidence. It's a consequence of tidal locking. The Moon rotates on its axis at exactly the same rate it orbits Earth, once every 27.3 days. This synchronization means that one hemisphere, the near side, permanently faces Earth, while the other hemisphere, the far side, permanently faces away. The far side was completely unknown to humanity until October 3, 1959, when the Soviet Luna 3 spacecraft swung around behind the Moon and transmitted the first grainy, low-resolution photographs of its hidden face back to Earth. What those photographs revealed was shocking, and 6 decades of subsequent observation have only deepened the mystery. The far side looks nothing like the near side. The near side is dominated by the Maria, those vast, dark, smooth plains of basaltic lava that cover roughly 31% of the surface. The ancients called them seas because they thought that's what they were: oceans and lakes and bays on a watery world. They're actually frozen lava fields, the remnants of volcanic eruptions that flooded giant impact basins between roughly 3.9 and 3 billion years ago. The near side has Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, Mare Crisium, Oceanus Procellarum. The names read like a poem of imagined oceans. The dark Maria are what give the man in the Moon his face. The far side has almost none of this. It is overwhelmingly bright, heavily cratered highland terrain. Where the near side is smooth and dark, the far side is rough and light. Where the near side bears the scars of extensive volcanism, the far side looks like it was subjected to the same bombardment but never experienced the volcanic flooding that resurfaced the near side. The asymmetry is dramatic. The Maria cover roughly 31% of the near side but only about 2% of the far side. Why? This is one of the longest-standing unsolved problems in lunar science, and despite decades of study and multiple competing hypotheses, we still don't have a definitive answer. The most straightforward explanation involves crustal thickness. Grail data confirmed what earlier missions had suggested. The far-side crust is significantly thicker than the near-side crust. On average, the near-side crust is about 30 kilometers thick, while the far-side crust averages about 50 kilometers. In some places, the difference is even larger, up to 25 kilometers. This matters because the crust acts as a lid over the mantle. For magma to reach the surface and create Maria, it has to punch through that lid. A thicker lid means more resistance, more rock to melt through, higher pressure required. The far side's thick crust effectively bottled up the magma that was trying to reach the surface. But this just pushes the question back one level. Why is the far side crust thicker? Several models have been proposed, and none of them is entirely satisfying. The tidal heating hypothesis suggests that in the moon's very early history, when it was much closer to Earth, perhaps only 15 to 20,000 kilometers away, compared to its current distance of 384,000 kilometers, Earth's gravity generated enormous tidal heating in the near-side hemisphere. This preferentially heated and thinned the near-side crust, creating the asymmetry we see today. The asymmetric crystallization model proposes that the difference arose from the way the moon's original magma ocean solidified. When the moon first formed, it was largely or entirely molten, a global ocean of magma hundreds of kilometers deep. As this ocean cooled, minerals crystallized and either sank or floated depending on their density. Light minerals like plagioclase floated to the top, forming the anorthositic crust. But the crystallization may not have been symmetric. If heat from Earth's radiation preferentially warmed the near side magma ocean would have remained liquid longer, allowing more time for dense minerals to sink and less crust to accumulate. The far side, cooling faster, would develop a thicker flotation crust. A third, more dramatic hypothesis involves a collision. In 2011, Martin Jutzi and Eric Asfog proposed that the early moon had a companion, a smaller body about one-third its diameter that formed from the same giant impact debris. This companion orbited in a gravitationally stable position for tens of millions of years before it eventually drifted out of stability and collided with the moon at low velocity, essentially a gentle cosmic rear-ending. The smaller body didn't form a crater. Instead, it pancaked across one hemisphere, adding a thick layer of crustal material that became the Farside Highlands. This big splat hypothesis elegantly explains the crustal thickness asymmetry, the absence of Farside Maria, and some of the compositional differences between the two hemispheres. But it requires a very specific set of initial conditions that may or may not be realistic. Testing these models requires data that we don't yet have, detailed seismic profiles of the Farside crust, samples from Farside Highland regions at multiple locations, and better constraints on the composition and age of the deep crust. China's Chang'e 4 and Chang'e 6 missions have begun to provide some of this data, but we need much more. Artemis-era missions, combined with robotic exploration of the far side, will eventually give us the answers. But the far side has its own specific anomaly that dwarfs everything else in scale and strangeness: the South Pole-Aitken Basin. This feature is, by any measure, one of the most extraordinary geological structures in the solar system. It is roughly 2,500 kilometers in diameter. You could fit the distance from Boston to Miami inside it. It is up to 8.5 kilometers deep, making it the deepest recognized impact structure on the moon and one of the deepest in the solar system. And it is old. Radiometric dating of samples that may be associated with the impact suggests it formed approximately 4.3 billion years ago, within the first 200 million years of the moon's existence, during the chaotic tail end of planetary formation. The impact that created South Pole-Aitken must have been cataclysmic beyond imagination. The impactor was probably 200 or more kilometers in diameter, a small world in its own right, roughly the size of the state of Massachusetts. It struck the far side of the moon at a velocity of tens of kilometers per second, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. The impact excavated clean through the lunar crust and deep into the mantle, exposing material from tens of kilometers below the original surface. It may have temporarily created a magma lake hundreds of kilometers across and many kilometers deep. The shockwave would have been felt on the opposite side of the moon. And yet, for all its violence, the basin was not completely destroyed by subsequent impacts. Still there, still recognizable, still telling its story to anyone with the instruments to read it. The floor of the basin is enriched in iron and thorium compared to the surrounding highlands, consistent with excavation of mantle material. The interior has been partially resurfaced by later volcanic activity, but not to the extent seen in the near-side Maria, another consequence of the far side's thick crust inhibiting volcanic eruption even in this enormous wound. But the most remarkable thing about South Pole-Aitken was discovered in 2019 by Peter James and colleagues using Grail gravity data. Beneath the basin, roughly 300 kilometers below the surface, they detected an enormous anomalous mass, a concentration of dense material large enough to produce a measurable gravitational signature from orbit. The anomaly has a mass estimated at approximately 2.18 quintillion kilograms. That's 2.18 times 10 to the 18th power kilograms. To give you a sense of scale, the researchers compared it to a volume of metal 5 times the size of Hawaii's Big Island embedded in the lunar mantle. What is it? The leading interpretation is that it's the metallic core of the impactor itself, the remains of the asteroid or protoplanet that carved the basin 4.3 billion years ago. When a metallic body this large hits a rocky target at cosmic velocities, the impactor doesn't simply vaporize and disappear. Computer simulations show that a significant fraction of the impactor's iron-nickel core can survive the collision, sinking into the target's mantle and remaining there as a distinct, dense mass. The moon, in this interpretation, is carrying inside it the corpse of another world, a fossil embedded in its flesh, a memento of the catastrophic violence that characterized the solar system's youth. If this interpretation is correct, and it's not the only possibility, the anomaly could also be explained by unusual concentrations of dense oxide minerals in the mantle, produced by the solidification of the ancient magma ocean. Then the South Pole Aitken mass anomaly is a direct window into the composition and structure of the projectiles that bombarded the inner solar system during its earliest history. By studying this mass, its composition, its geometry, its density, we can learn about the building blocks of planets. We can learn about the process by which small bodies merge and differentiate into layered objects with metallic cores and rocky mantles. We can learn about the violence that shaped the worlds we know. China's Chang'e 4 lander, which touched down inside the South Pole Aitken Basin in January of 2019, was the first spacecraft to explore this extraordinary feature from the ground. Its rover, Yutu-2, has spent years trundling across the floor of the von Karman crater, a 186-kilometer-wide crater within the larger basin, analyzing rocks and soil that may contain material excavated from deep within the lunar mantle by the original basin-forming impact. Early results from Yutu-2's visible and near-infrared imaging spectrometer revealed the presence of low-calcium pyroxene and olivine, minerals characteristic of mantle-derived material. This was exciting because it suggested that the rover was sampling rocks that had been dredged up from deep inside the moon by the enormous impact. But the story quickly became more complicated. The mineral abundances didn't perfectly match the predictions of simple mantle excavation models. There was less olivine than expected. The compositions suggested a more complex geological history than a clean scoop of pristine mantle. Some researchers proposed that the surface had been contaminated by material thrown in from nearby impacts. The von Karman crater is, after all, nested within the larger basin, and its own formation would have mixed in additional crustal material. Others suggested that the mantle itself might not be as compositionally homogeneous as the models assumed, that different regions of the mantle might have different mineral proportions, depending on how the original magma ocean crystallized. And then Chang'e 6 went even further. In 2024, China's Chang'e 6 mission achieved something unprecedented: a sample return from the far side of the moon. The spacecraft landed inside the Apollo Basin, a 300-kilometer-wide impact structure within the South Pole Aitken Basin, collected approximately 1.9 kilograms of soil and rock fragments, and returned them to Earth in June of 2024. These were the first farside samples ever collected and returned. They are currently being analyzed by laboratories around the world, and preliminary results have already yielded surprises. The samples appear to be composed of a mixture of local basaltic material and material ejected from more distant impacts, with ages and compositions that are helping to pin down the timeline of volcanic activity in the South Pole Aitken region. Full results will take years to emerge, but they promise to revolutionize our understanding of the moon's far side. All of this, the mascons, the moonquakes, the water ice, the swirls, the farside asymmetry, the South Pole Aitken mass anomaly, the transient phenomena, brings us back to the present moment, back to Artemis II, back to 4 humans in a spacecraft, traveling farther from Earth than anyone has been in over half a century. Artemis II is not landing on the moon. That comes later. Artemis III is the mission that puts boots on the surface, targeted for the South Polar region, one of 13 candidate landing regions near craters like Shackleton, de Gerlache, connecting Ridge, Nobile, Hayworth, and others. But Artemis II is doing something that hasn't been done in over 53 years. It is putting human eyes, human judgment, human perception, and human intuition back in the vicinity of the moon. And there is a reason that matters beyond mere symbolism. Instruments are extraordinary. I love instruments. I've spent my career designing, building, deploying, and interpreting data from scientific instruments. Robotic spacecraft have revolutionized our understanding of the moon and every other body in the solar system. No sane scientist would argue otherwise. But there are things that human observers notice that instruments miss. Apollo astronauts consistently reported features and phenomena that hadn't been predicted from orbital photographs, that hadn't shown up in spectral data, that no robotic camera had captured. They described the way the regolith sparkled like fresh snow when the sun was at a low angle, a phenomenon caused by the glass beads in the soil acting as tiny retroreflectors. They described the horizon glow, a mysterious luminosity above the western horizon just before orbital sunrise, which may have been caused by electrically charged dust particles levitating above the surface. They described the disorienting lack of atmospheric haze that made distant mountains look close enough to touch, confounding depth perception in a way that no amount of photographic analysis had prepared them for. Gene Cernan, the commander of Apollo 17, the last person to walk on the moon, described seeing what he called orange soil at the Taurus Litrove landing site. It turned out to be volcanic glass beads, tiny spheres of titanium-rich basalt that had erupted from a fire fountain 3.7 billion years ago and preserved their vivid orange color all that time. No orbital camera had detected them. No spectrometer had flagged them. It took a human eye, trained in field geology, glancing at the ground while walking between sampling stations, to notice something anomalous and stop to investigate. Human perception is a scientific instrument, and we haven't been flying it in the vicinity of the moon since December of 1972. The Orion spacecraft that carries the Artemis II crew is, of course, loaded with cameras, sensors, and communication equipment that vastly surpass anything Apollo carried. The crew will conduct systematic visual observations of the lunar surface, test the spacecraft systems for future landing missions, evaluate radiation exposure inside the deep space cabin, and push the environmental control and life support system to its limits with 4 occupants for the first time. The mission will last approximately 10 days, during which the crew will loop around the far side of the moon, passing within about 7,000 kilometers of the surface, and return to Earth on a free return trajectory. But perhaps the most important thing Artemis II accomplishes is not any single observation or measurement. Its validation proves that the architecture works. It proves that the Space Launch System can launch humans beyond low Earth orbit. It proves that the Orion capsule can support a crew in deep space and survive the punishing re-entry into Earth's atmosphere at roughly 25,000 miles per hour, significantly faster than a return from the International Space Station. Everything that follows, the landings, the surface habitats, the gateway station, the eventual journeys to Mars, depends on this mission going right. And let me tell you about Gateway, because it's central to the future of the anomaly-hunting lunar science I've been describing. The Lunar Gateway is a small space station that will orbit the moon in a near-rectilinear halo orbit, a highly elliptical path that brings it as close as about 1,500 kilometers to the lunar surface at its nearest approach and swings it out to roughly 70,000 kilometers at its most distant point. This orbit was chosen for several reasons. It's gravitationally stable, requiring almost no fuel to maintain. It's accessible from Earth using the Orion spacecraft, and it provides periodic close approaches to the moon that enable surface operations at a wide range of latitudes, including the South Polar region. Gateway will serve as a staging point for surface missions. Astronauts will travel from Earth to Gateway in Orion, transfer to a lunar lander, currently being developed by SpaceX as a variant of their Starship vehicle, descend to the surface, conduct their exploration, return to Gateway, and then take Orion home. This architecture allows multiple surface sorties from a single orbital platform, extending the duration and scope of lunar exploration far beyond what Apollo achieved. But Gateway is more than a docking port. It's a laboratory. It will carry instruments to study the deep space radiation environment, critical for understanding the health risks of long-duration spaceflight beyond Earth's protective magnetosphere. It will serve as a platform for communications relay, enabling continuous contact with assets on the far side of the moon. And it will support telepresence operations. Astronauts aboard Gateway will be able to control rovers on the lunar surface in near real time, with communication delays of only a fraction of a second, compared to the approximately 2.5-second round-trip delay from Earth. Imagine the possibilities. A rover parked at the rim of a permanently shadowed crater near the South Pole. An astronaut aboard Gateway, wearing a virtual reality headset, drives the rover into the darkness, into a place where sunlight has not fallen in 2 billion years. The rover's headlights illuminate the interior. Its drill bites into the regolith. Ice crystals glitter in the beam. The astronaut, 60,000 kilometers overhead, feels the resistance through haptic feedback in the controllers. They extract a core sample. They seal it in a container. A few days later, another rover retrieves the sample and carries it to an ascent vehicle that brings it to Gateway for analysis. Or picture this: a network of seismometers deployed by multiple Artemis surface missions, spread across the South Polar region and eventually across the entire near side. The data streams up to Gateway, where it's processed and relayed to Earth. Scientists in Houston, Pasadena, Boulder, and Tucson monitor the data in real time. A shallow moonquake registers on 3 stations simultaneously. Its location is triangulated to within a kilometer. It falls directly on a lobate scarp identified in LRO imagery. Within hours, a mobile rover is dispatched to the scarp to look for fresh ground disturbance. Cracked regolith, displaced boulders, newly exposed bright material. For the first time in history, we're doing active geological monitoring on another world. Or consider this scenario. A magnetometer-equipped drone, a small, solar-powered hopping vehicle, lands in the center of Reiner Gamma. It measures the magnetic field at the surface, centimeter by centimeter, building a map of the field structure far more detailed than anything achievable from orbit. It collects soil samples from the bright swirl center and the dark surrounding terrain. Spectroscopic analysis reveals the differences in space weathering between the two. The magnetic field measurements show that the field has fine-scale structure, filaments and loops and cusps that correspond precisely to the swirl patterns visible from above. The magnetic sunscreen hypothesis is confirmed, or falsified. Either way, we know. After 60 years of speculation, we finally actually know. These scenarios aren't science fiction. They're engineering plans. They're in development. Hardware is being built. Software is being written. Astronauts are training. The timeline is aggressive, probably too aggressive, as space program timelines always are, but the direction is clear. We are going back to the moon not for a visit but for a stay. Not for flags and footprints but for answers. And the timing matters because we are not alone in this endeavor. China's lunar program has been executing a methodical, strategic, brilliantly managed campaign of exploration that represents the most impressive national space program since the Apollo era. Chang'e 1 orbited the moon in 2007. Chang'e 2 followed in 2010 with higher resolution imaging. Chang'e 3 landed on the near side in 2013 with the U2 rover. Chang'e 4 achieved the first far-side landing in 2019. Chang'e 5 returned near-side samples in 2020, the first lunar sample returned by any nation since the Soviet Luna 24 in 1976. Chang'e 6 returned far-side samples in 2024. And the roadmap extends further. Chang'e 7, planned for 2026, will target the South Polar region with an orbiter, lander, rover, and a small flying probe designed to hop into permanently shadowed craters and search for water ice. Chang'e 8, planned for around 2028, will test technologies for in situ resource utilization, manufacturing useful products from lunar materials. China has announced plans for a permanent international lunar research station at the South Pole, with construction beginning in the early 2030s. India is continuing its Chandrayaan program, with Chandrayaan-4 aiming to achieve an Indian lunar sample return. Japan's space agency, JAXA, is developing the LUPEX mission in collaboration with India, targeting the South Polar region with a large rover equipped with a drill to search for subsurface ice. The European Space Agency is contributing technology and instruments to both the Artemis program and independent lunar missions. South Korea's KPLO orbiter has been studying the moon since 2022. The United Arab Emirates plans to land a rover named Rashid 2 on the moon. Commercial companies Intuitive Machines, Astrobotic Espace, Firefly Aerospace are developing lunar landers under NASA's Commercial Lunar Payload Services program, providing frequent, relatively low-cost access to the surface for scientific instruments. The moon is becoming a busy place. And this convergence of national and commercial interest, this new lunar rush, is driven fundamentally by the same set of anomalies and mysteries I've been describing. The water ice, the geological activity, the unique scientific record preserved in the ancient surface, the resource potential, the strategic value. Everyone is going back to the moon because the moon, it turns out, is far more interesting, far more useful, and far more mysterious than anyone realized when the last Apollo astronaut climbed back into his spacecraft in December of 1972 and left. Let me bring this back to the biggest picture I can frame because I think it matters. The moon is not just a rock in the sky. It is a record, a 4.5 billion-year-old record of everything that has happened in this corner of the solar system since the planets formed. Its surface is a chronicle written in craters and lava flows and regolith layers and trapped volatiles. Its interior is a laboratory of planetary physics. Its relationship to Earth, the tidal coupling, the orbital evolution, the stabilizing influence on our planet's axial tilt, is a case study in how moons shape the habitability of the worlds they orbit. The giant impact that created the moon, the collision between the proto-Earth and the Mars-sized body Theia, roughly 4.5 billion years ago, was the most consequential event in our planet's history. It gave us a large, stabilizing moon. It may have contributed to the formation of Earth's metallic core. It set the stage for plate tectonics, for a stable climate, for the conditions that allowed life to emerge and persist. Understanding the moon is, in a very real sense, understanding ourselves. Understanding how we got here. Understanding why Earth is habitable and Mars is not. Understanding the thin chain of contingencies, a particular impact at a particular angle at a particular time, that led to a planet where liquid water could pool, where organic chemistry could flourish, where single cells could become forests and fish and philosophers. The moon is also a time machine. Earth's active geology, its plate tectonics, its volcanism, its erosion by water and wind and ice, has erased almost all evidence of our planet's first billion years. The oldest rocks on Earth are about 4 billion years old, and they are rare, metamorphosed, hard to interpret. The geological record of the Hadean Eon, the first 500 million years of Earth's existence, is almost entirely gone. But the moon preserves it. Every crater on the lunar surface is a timestamp, a record of an impact that tells us about the population of asteroids and comets at the time it formed. The oldest craters date back over 4 billion years, to the epoch of the Late Heavy Bombardment, a period roughly 3.9 billion years ago when the impact rate in the inner solar system spiked dramatically, possibly due to the gravitational reshuffling of the giant planets. Some researchers believe this bombardment sterilized Earth's surface, resetting the clock for the origin of life. Others argue it delivered the very water and organic molecules from which life arose. The moon's cratering record is our best, perhaps our only window into this violent, formative period. And then there are the cold traps, the permanently shadowed regions at the lunar poles, where temperatures plunge to 35 Kelvin, minus 238 degrees Celsius, making them among the coldest places in the entire solar system, colder than the surface of Pluto, colder than the dark side of Mercury's poles, colder than most of interstellar space. These natural deep freezers have been collecting volatile molecules for billions of years: water, carbon dioxide, ammonia, methane, simple organic compounds, delivered by comets and asteroids, outgassed from the interior and planted by the solar wind. By sampling the ice in these craters, we can potentially reconstruct the composition of the cometary flux that swept through the inner solar system during its earliest history. We can determine the origin of Earth's water. Was it primarily delivered by carbonaceous chondrite asteroids, or by comets from the outer solar system? We can search for prebiotic organic molecules, the amino acids, nucleobases, and other building blocks of life that are found in meteorites and that may have seeded Earth's primordial oceans. The permanently shadowed craters are archives, libraries, time capsules, and Artemis is going to open them. This is what the Artemis program is really about. Not just exploration for its own sake, though that would be reason enough. Not just national prestige or geopolitical competition, though those forces are undeniably at play, and honestly, if competition between nations drives faster progress in lunar science, I'll take it. It's about using the moon as a laboratory, a natural laboratory 240,000 miles away, where the answers to some of the deepest questions in planetary science, in all of science, are written in rock and ice and magnetic fields and gravitational anomalies, waiting to be read by anyone with the curiosity, the courage, and the technology to go and look. So as Artemis II orbits, as Reed Wiseman and Victor Glover and Christina Koch and Jeremy Hansen look out their windows at a landscape that no human eyes have seen at this distance in 53 years, I want you to think about what they're seeing. Not just a barren, gray, cratered world. Not just a dead rock. They're seeing a world full of secrets. A world with water ice in its shadows and lava tubes beneath its surface that could shelter future habitats from radiation and meteorites. A world with magnetic tattoos that we still can't fully explain. A world with unexplained mass concentrations buried beneath ancient lava plains. A world that is still cracking, still quaking, still exhaling traces of gas from deep within its interior. A world that carries embedded in its mantle the metallic remains of the asteroid that nearly destroyed it 4 billion years ago. A world whose permanently shadowed craters may contain a frozen record of the solar system's earliest chemistry, the raw ingredients from which life itself emerged. They're seeing all of that, and they know because they're scientists and pilots and explorers, because they've studied and trained and prepared for years, that what they're looking at is not a destination. It's a beginning. It's the first step back to a world that we visited briefly, long ago, and barely scratched the surface of understanding. Soon, sooner than most people realize, probably within the next few years, humans will stand on the surface of the moon again. They'll stand at the rim of a permanently shadowed crater near the South Pole, a place where the sun hangs perpetually near the horizon, never rising more than a degree or two above the jagged crater rims, casting shadows that are millions of years old. They'll look into a darkness that hasn't been touched by sunlight since before the first dinosaurs walked on Earth. And they'll take a step forward, into the dark, into the cold, into the unknown, because that's what we do. That's what we've always done. We are a species of explorers. We left Africa. We crossed oceans. We climbed mountains. We went to the moon. And then we stopped. For 53 years, we stopped. We told ourselves it was too expensive, too dangerous, too far, too hard. We told ourselves the robots could do it better. We told ourselves we had more pressing problems at home. All of those things were true. All of those things are still true. And none of them matter, because the anomalies are out there, waiting. The mascons and the moonquakes and the water ice and the swirls and the mass beneath South Pole Aitken and the gas leaking from ancient fractures. They've been waiting for us for 4.5 billion years. They are patient. They are not going anywhere. But neither are we. The moon has been hanging in our sky since before there were eyes to see it. Since before there was an atmosphere to see it through. Since before the continents had assembled into their current shapes. It has watched, impassive and silent, as life crawled from the oceans, as forests spread across the land, as primates descended from the trees and began to look up and wonder what that bright disk in the night sky actually was. And now, finally, after billions of years of waiting, we're going back to find out. But before we get too swept up in the grand vision, let me bring you back to the science, because there are more anomalies to discuss, and some of them are among the strangest things we've ever detected on any planetary body. Let's talk about the lunar dust, the regolith, and why it might be one of the most hazardous materials that future astronauts will encounter. The lunar regolith is not like any soil on Earth. It has never been weathered by water. It has never been rounded by wind. It has never been softened by biological activity. Instead, it has been pulverized by 4.5 billion years of relentless micrometeorite bombardment. Tiny particles, most of them smaller than grains of sand, slam